Yeah, I saw it.
Hey, tonight I want to talk to you a little bit about time, and it goes over several chapters, but I want to talk to you about some of the things that are are involved with setting up of time in the program controller. Just right there, Stein. Yeah, thank you. So we're getting close on the April 1st date, and like I said, I would give you a couple more days after that. Let's just tie it down. Some of you are counting on the weekend, and I will give you the weekend if you're. So anything to me by April 6th in my hand here at this will be accepted. Okay, April 6th here at 5:30 will be accepted, and after that it will be not accepted. So the drop dead date is 5:30 on April 6th for the 20 points. Any questions? Any comments? Thank you. I know that's a gift, but it's on the other hand, the way that the weekend splits. I'm not going to be here on Friday, so I don't plan on doing too much on Friday. Please give me that day off. Anyway, so I want to talk to you a little bit about time and time-related events. And I've got some of them are stories, and some of them are not. So let's look at chapter 8. So in chapter 8, we talk about math functions, and I talk about at the end of this chapter a a lab. That's the first 4-point lab that you have, and it involves these little guys right here. Can I have your attention, please? This is for your use. This is not necessarily a. This is a lab that you can do. Now, one of the things that Siemens has over Allen Bradley is in this box they do several things that you can't do with the Allen Bradley. And the little Allen Bradley can do everything that Siemens can do. Siemens can do everything that Allen Bradley can do. But at this level, they can't do a pulsed output like Siemens does. Okay, this is a very difficult task to do, and an Arduino can do it, but the poor little Allen Bradley can't do it. So basically, what you have to do here is to if you're going to control one of these guys, and there's several of them laying around. If you need one, I can get you one. But this is a I'll show you the actual pulse train that comes into this thing. Now, this is a pulse width modulated signal, and what you have to do is you have to put a width of the pulse in. Okay, so can everybody see that? Is that a little too small? Maybe I can put that a little bit bigger. But anyway, that is a pulse. Okay, now you have to put this pulse in every 200 milliseconds, and the width of that pulse determines the position of the arm. All right? Does everybody understand the basic concept? So you have to create a pulse of width such and such over a length of time. I think it's 200 milliseconds, but let me just look and see. I think it is over it's a 200 millisecond. I believe this time duration is 200 milliseconds. And that is configurable. This time duration, TED, is in, I think, 200 milliseconds. Let me see what it is for sure. Here it is. It tells you what it is. And One-sided pulse traveling 1500 to 1900 microseconds. So that's 1.5 to 1.9 milliseconds. And this is over a period of time of, I think, 200. The pulse time is, I think, 200 milliseconds. Okay. Don't quote me right on that, but I think that's what it is. You might want to look that up. But that's, does anybody see that for sure? Does anybody see that 200 milliseconds in here? It's, this is the full time limit. I think from the start of the pulse to the start of the next pulse is 20 milliseconds. This time right here is, I think, 20 milliseconds. Boy, I can't, it doesn't say, but I think it is. Okay, so I think what you have to do is provide a pulse that is 20 milliseconds in length, and then you give it a number that is a percentage of that 20 milliseconds. And that's typically what you have to do with these things. And I think that is it. Now, the pulse duration is from 0.9 to 2.1. With a 1.5, the pulse refreshes at 20 milliseconds. There it is. So every pulse, every 20 milliseconds, you have a pulse. Okay, so you have a pulse of certain duration, and then 20 milliseconds later, you have another pulse of certain duration. Now, this is by definition how these things are built. Okay, so this is 20 milliseconds. Now, the way to get the pulse from 24 volts down to 5 volts is you build a voltage divider, and this is what that is. This is a voltage divider. You take the output of the PLC, you put a 3.6K resistor in, and that goes to your pulse, and then that goes to your signal, your PWM signal. Then you put a 1K to ground or to your 0 volts, okay? And then you also put a 5 volt to the red or the middle, and then that will give you use a power supply for this, a 5 volt power supply for this, and that will give you control. Now, how do you set this up? That's the basic question. How do you set it up? You have to set up a signal off of the PWM input, and that gives you a control of this. And here's how you configure that. When you're setting up your under general, under your PLC, under properties, you come down here and you set up a PWM output, and this is how that's done. Okay, and you set it up to a cycle time, and you set it up to an output, and you basically everything goes in there. The 2000 goes in there. Okay. So this is a attempt to set this thing up and get it to work. Now, what you've got to do is you have to vary this length. And what you do not want to do is you don't want to slam it. In other words, you do not want to build in you're here and then all of a sudden you're there, and they will do it, but it's very hard on them. So what you want to do is you want to build a ramping signal that does this. Okay? So how do you do that? Well, you have to basically have a timer and a counter, or a timer and an add block that goes from this number to this number. And then when you're going back to the other, it goes from that number to that number over a period of time. So what you do is you have a a timer that when it turns on, it's like this would be a TON, this would be T1, T1 dot done, or T1 dot Q and your enable would be out here. So basically this thing just sits there and it pulses, and what it does is it pulses at the speed that you want it to pulse at, and then this, every time it does that, it adds or subtracts to this number until you get to this number and you stop. So it basically, it does this. It does this. It's really, what you're seeing here is little steps. You do that? That's easy. It's a 4-point lab. Now the hard part to get to work is this part up here, which looks simple, but it is not the simplest thing in the world to set up and do. And that is this part right here. But you can do that, and you can set this thing up, and it will work. Okay? And not only that, it will, you have to have a PWM block, and it shows you how to set up your PWM block. This has got to be set up in your program. Is available, and it's got to be set up. This has to be done. You cannot get along without setting this up. You got to set up this here in your configuration, and then you have to add this in your program. And then you can go and you can add to your number, and you can actually set up the minimum and the maximum, and it actually moves. If you put the number into this QW 1000 word, it will go between the min and the max, and you can see the thing turn. It's a very interesting lab, a very nice lab. And like I said, if you do not have a one of these that is good, I can give you some. I've got some sitting on my desk that are good. Okay. Does everybody understand what this is about? You're actually doing a PWM block that either is a little skinny or a little bit wider. This doesn't vary by much. It might vary just a little bit. Now this might be this might be all the way left. This might be all the way right, and this might be the center point. It's very, very subtle, very small differences, and that every time it does that, it goes to that point. So if you want to gradually move from one point to the other, you have to do this addition or the subtraction to get it from one number to the other number. And this would be adding, and this would be subtracting, going back to that number. It works. It works very, 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 very well. So if you're interested in doing that lab, it's a 4-point lab. It can be set up very quickly. The wiring is easy. You have to do this. And then you're in. Okay, that's about it. So that's a timing lab. It's a timing lab in that you have to set up, the cycle time is 20,000 microseconds. There's where the 20,000 is. You have to set all this stuff up. You have to then tie it to an output. And how do you test to see if it works? What's your dividing point? If you see the output flashing on little, you won't see it a lot because it's only on a very small part of the time. But it'll be very weak or very, very dim, but you'll see the output on. The green light will be on. If you don't see the green light at all, it isn't working. And the distance between the low end and the high end is not 20,000. It's like, and it tells you in here how to modulate from one extreme to the other. It tells you the limits of it. And they're all the same. Believe it or not, they're all the same. That you don't get one set for one and I have to go wait to another set for another one. They all work the same way. They all work off of the same device. Okay, so that's a very good lab, and it works very, very, very well. Now, another lab that you can do that has to do with somewhat with timing is the lab in chapter 19, which we're talking about with the PLCs. Now, this is kind of a weird way of getting you to chapter 19 because several people have been asking me about the labs in chapter 19, which are really, there's two labs, the ball and tube and the tank over tank lab. And I want to talk about those labs because they are, well, we have problems with the one. We really have problems with both of them. They both have some weaknesses, but you can do both of them. You can do either or both of them if you want. And I'll accept something less than I'll accept something less than perfect. How's that? And I understand that you're trying to get as many points as you can at this point in time, but I'll accept, I'll accept a partial as a full grade in these labs because I understand that you're, and I'm not saying that because I'm a good guy. I'm saying that because I know that if you try these labs and they don't work, they get very frustrating. But they both of them are good labs. And I want you to, they're both worth 8 points. Now, we don't talk a lot about the the insides of the PID block, but it has to be executed on a clock. So if you are trying to make something work and you're doing a calculation and you're trying to say, okay, now every so many seconds or every 5 seconds or whatever, every millisecond or every 5 milliseconds or whatever, I expect that I can make an algorithm. You expect that algorithm to be right on the money. You do not expect to have to you don't expect to have to wait. You don't expect to have to you expect it to be crisp, okay? So if you're looking at at a program like this PID program, and it's doing a calculation, you expect it to calculate on a clock, okay? Now, there's really 2 ways of doing this. You can have your program and then have a timer, and then when the timer times out, you can execute the block. That's not the preferred way to go. The preferred way to go is to create an OB that is basically a timed OB. And that's what we have with these 2 programs. Both these programs have a time-based program, and I'll show them to you right here. Both of them do the same basic thing. So I'll just use version 18, I guess. And this is this computer has 18, 19, and 20. My older one has version 16 on it. So I've kind of hedged my bets, but this is the only thing I've got on this one. But I wanted to show you how that works. So basically, I got to go find it. So let's go get it. Give me a second here. I'm sorry I didn't get it extracted earlier. I'll get it. Okay, so this is the ball and tube 23. And I got to go back and pick it up. So I'm going to go back here and browse and get it. I want to show you how it executes and why it takes time for it to execute. I also want to show you how to build a faceplate in this lab. I know I didn't do a very good job of telling you how to build a faceplate before, and I just kind of hope that you would get it on your own. But it isn't hard, but it takes a little bit of time to do that, and I'll try to do that as well. But two points for doing this, or two reasons for doing this. I wanted you to understand the timing of it, and also to understand that you can build a faceplate pretty straightforward from it. Okay, so let's go and look at it for a minute and study okay, so here is the actual blocks. Can everybody see that? Now, OB30 is not OB1, right? Everybody's got that, right? Now let's look and see what OB30 looks like. This is the one that does the execution of the PID block. And OB30 is on a clock, and every 10 milliseconds this puppy executes. Okay? Right on the money, right? Every 10 milliseconds this guy executes. All right, so now let's look at it for a second. Now, what do you have? You have the input and the output, and then you have the PID block itself. Okay, and that basically is all you have to do here. Now, what do you not have to do in OB30? The things that have to do with getting the information in and the information out, the HMI interface part, you don't have to do that here. But you want to just do the minimum that you have to do in the time block. Then you get in and you get out. Now, the nice thing about this processor is all the I/O are right immediate I/O. If you have a processor with I/O cards that are attached, then the I/O isn't immediate. In other words, if I need an input or an output, an analog signal, I just go grab it right now. Whenever it is that I need it, I grab it and I go. But if you have to go across a backplane to get it, you have to plan on when you get it, and it has to be fresh. So this is OB30. Let's look at the properties of OB30. See what it says. All right, it's a cyclic interrupt. It's a SIC interrupt, right? Cyclic interrupt. And let's see how often it executes. Well, there's timestamp. Let's look at this information. Okay, and the timestamps. Let's just look at and see what it says. Okay, it is every what? 20 milliseconds. Does everybody read that? So every 20 milliseconds this executes. I thought it executed every 10 milliseconds, but it doesn't. I have taken this up to 50 milliseconds and the ball starts to go unstable. So if that tells you anything, that's a quick acting PID block, okay? But there it is. Every 20 milliseconds, this clock comes in and executes and does this program. And the I/O are immediate. They look at the input, they do the output, they do them immediate because it's all tied right into the processor. But if it's not tied into the processor, it has to go across a backplane, you have to guarantee that it is fairly fresh. In other words, that I/O is fairly up to date. Now, you do have the opportunity with all these processors to stop what you're doing, go out and read that I/O point, and then bring it back. So that's called an immediate read. So you can do that. We don't have to do that here because they're all immediate. But if you understand what I'm saying, if you go across a backplane to another card, then you have to basically say, give me that information as quickly as possible. I want information that is up to date now. Every 20 milliseconds, you want to execute this. And you've got to accept that it might not always be right on 20 milliseconds, but as close as you can get it to 20 milliseconds. Because if you don't execute on 20 milliseconds, if let's say you average 10% off, and you had an algorithm that is going along and it's doing its thing, if you're 10% early one time and 10% late the next, that upsets the algorithm because the algorithm is built on even clock cycles, taking samples at even points. And here's a case in point where that might not be the case. You have to be careful that you create a situation where they're as good as possible. Sometimes you don't care. If it's temperature in a glass furnace, they do this once a minute. They do a PID block update once a minute. Now, do you think they care if they're a tenth of a second off? Not really. But here, if your analog value is from a little bit before or a little bit little bit too late or whatever, you're sacrificing the accuracy of your system if you don't take this into account. Okay, and cyclic interrupts are very, 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 very important. Okay, now I'm going to tell you this is gets into a story that it's going to take a little bit of time to tell, but it's well worth it. And I don't believe I've told you the story. If I did, I'm sorry, but I probably if I told you anything, I may have told you little bits and pieces of it, but I didn't tell you the whole story. This is from my first job in industry. They had a glass furnace that they were going to build in Laurinburg, North Carolina, and basically they had a line where you're bringing glass down like this, and then it can go either this way or this way or this way, okay? And then it can go out here or out here, or it could go on down the line. So basically you had glass, pieces of glass, flat glass like is in a window glass, pieces like this coming down, and then going to this corner, and then had to make a decision whether it's going left, right, or through, and all that kind of stuff. And then left, right, through, it had to go down to here. And you could even break these little pieces into littler pieces, and then some of them could go this way, and some of them could go this way, and all that good stuff. Beside the point, this was based on a pulse generation package, a pulsar that actually did a pulse like this, a square wave pulse. Now, the original process was they had originally designed this based on a leading edge interrupt. And the guys that did this, this is a computer system, not a PLC, but a computer. But it was in 1973 time. It was the cycle time. Every instruction was done every 400 nanoseconds. Okay. So a cycle in the computer was every 400 nanoseconds. If that tells you anything about the speed of the computer, it was a dog. And it was 16K of RAM that was running in it. 16K of RAM. And how much do you think it cost? Any guesses? $1973? Yeah. 16K, 400 nanosecond instruction cycle time. And it had some I/O on it. It looked like it was about like the size of a refrigerator, a cut refrigerator, about 4 feet tall refrigerator, and that was it. So how many of you want to? How would you like to sell? How would you like to have been the salesman on that job? Anyway, they used interrupts. They used every pulse that came in. They did a leading edge interrupt, but they were only doing 7 sections, and that was in Rossford. So then we went to Laurinburg, and they had 66 of these pulses coming in. And the guy that was the leader, he believed that the interrupt was the way to go. And he got into a fight, not physical, but he got into a verbal fight with the main manager of the project, and he quit. And that left a big void in the project because he was the main guy. I was kind of his understudy. If you would have said he would have stopped in mid-stride, I would have run into him because that's how close I was following his instruction and everything else. The other guy that was on the job had worked with John, was number 1. Ken was number 2. Ted was a late number 3. Okay, I was the third guy in the project, and I had not done any of this before. These 2 guys had done the first project where they just went to this point, and they'd done 7 sections of conveyor, and that was as far as they went. 7 sections of conveyor. So this guy gone. The plant at Rossford said you cannot let him go to the new plant because it's going to be a non-union plant. They're going to try to drive it non-union. We don't want him there. If it's going to fail or whatever whatever it does, it's going to do it without Ken. So Ken did not go. Ken helped me for a while in Toledo, but then he basically could not go to the plant. So I went to the plant by myself, and I had written some of these programs, but I had looked at this input from the computer at Rossford, and I saw that with the 7 sections of conveyor, that the light showing the interrupt program was rather light. I mean, it wasn't burning out like it was that bright, but they had a little light on that level of program, and it was a hot program. It was running all the time. And I said, we're going from 7 to 66 sections. Will it work? Will I have enough time for the interrupt? And I didn't know, so I did not know. But I basically made a decision to do a scanned program. So I knew how fast these pulses came in, and I scanned the program a little faster than the rate of the pulses coming in. So if the pulses are coming in like this, I guaranteed that my program ran at least fast enough to pick up, like that. I was scanning faster than the width of the pulse, even at the fastest speed of the conveyor. Everybody follow what I just said? And it works, okay? Now, the side note of this whole thing was that I thought I was going to get fired because of this, and maybe I told you this part of it. Before I went to Laurinburg, I was at the lunchroom, or not at the lunchroom. I was at the vending machines with my boss, there was another John up here, but he did not know very much about anything other than he was the boss. Okay, he was the boss, but he was not privy to how this stuff worked. He's a smart guy, but he just did not know how this stuff worked. Well, anyway, in front of somebody else, somebody asked him, well, how's that program going to work down in Laurinburg? Is it with interrupts? And John said, oh yeah. And I corrected him. I said, no, I changed that to a scanned program. And you should have seen him walk away. It was like, uh-oh, I do think I just got fired. But they didn't have anybody else. They had no one else, okay? And he asked me then I went back to his office, I went back to my office. I knew that something was going to go on, and he asked me to flow chart it, and I did, and he accepted it. So anyway, I went down to Laurinburg, and it worked. It didn't work right away because my programs, there were too many things to do before I could get up to speed, and by that time, they had already started the line. So now they've started the line, and I can't check my programs out because they've got to run product. So they had to run in manual all this time that this was going on. And one day I walked in and I heard the crushers were down upstream. They're crushing glass up here. And I thought, what's going on? They said, somebody forgot to order the soda ash. Well, what is soda ash? I said, and I had no clue what it was. They said, well, you can't make glass without it. I didn't know that, but I smiled from ear to ear. I went down and told them, I said, now we're going to take that crusher and put it up so that I can try my programs. We'll put a crusher right here. There was a crusher right there and a crusher down here. And then and a crusher right here, and we're going to see if we can get around the corner. And by the end of those 2 days, I was rock solid on my program. My program ran. I knew it would run. I was okay. It was good to go, and everything about it worked. Now, I'll tell you another little side about this. I not only collected on leading edges, but I collected on trailing edges. So every transition was 0.75 inches. Every pulse was 1.5 inches apart. I was twice as accurate as they were with a scanned program, and my program ran a lot less intense light than theirs did. So it made me a firm believer in pulse, in not in interrupt-driven programs, but in pulse-driven programs. In other words, a scanned program every so often, as opposed to an interrupt-driven program. Interrupts take time. Every servicing of every interrupt takes time. And that's time that you don't have necessarily. So if you have a lot of them, you can slice it into something that is simple. You do that, okay? So I did that. Now, the other side of the coin is my philosophy in that era was this, and it still is. If you come to a situation like that where you know that you're going to get shot down, but you know that you have the right answer, if you are 100% or 90% or 95 or 98% sure, and I was pretty sure that I had a better answer, what do? You don't ask for permission, you ask for forgiveness. And I'm telling you, if I would have asked for permission, I would have never got it. I would have been told, no, you got to do it like John did it. And I don't know that it wouldn't have worked, but I know that mine worked, and it worked much better and much more accurately than the old system did. And from that point on, that's what they used. So, and again, I'm not trying to brag about what I did, but it worked. And I saw the problem, and I had the whatever to go ahead and make the change. Okay, enough on that. Now, the next phase of this is a little bit more interesting in that I got the thing up and running, and I told them, I said, now this is going to work. And they said, okay. Now, the foreman was up here, and there was an automated sheet that said where everything was supposed to go. It was supposed to go this way, supposed to do this, supposed to do that, and all that kind of stuff. But everything was automatic. Okay, everything was automatically generated. All the configuration was automatic. So I presented this guy with a sheet, and I said, now, this is what you're going to do. And he said, but my boxes are not over there, they're over here. And the cutter heads that you have that you're programmed, some of them aren't working. What now? Well, I had to start making some adjustments to my automated program. My automated program had to have a manual backup. And instead of having 6 HMI screens, guess how many I ended up with? Does anybody get the irony of this? A bunch of people not knowing what they wanted and saying that pie in the sky, and here comes along a dumb whatever, and I just kept plowing into it, and every time I plowed into it, what did I do? I had to fix it. In order for them to run, I had to fix it. All right? And eventually it worked, and eventually it worked okay, and it became the standard. All right? Now, through this or that or whatever, I got tired of thinking that I might have to do this again, because it took me 7 months of 12-hour days, 7 days a week to do this, to get this to run. And I didn't want to have that happen to me again. If I could help it, I didn't want that to happen to me again. So I would have listened to somebody if they came along and offered me another job, and finally somebody did. So I took it. Okay? And a year later I got laid off from that job. So go figure. But my point is this. I left, and then later on they built a second line. Now the second line, they took the idea that you've got all this power in this computer, you can do anything. Okay? They got the idea that you could do anything, right? Now, that's a dangerous position to be in. Okay, you can do anything. You have a computer, you can do anything with it, right? Isn't that right? They almost bankrupted the company with that philosophy. They built a second line in Laurinburg, and in the second line, they had the same kind of situation, except for the fact that they had all these operator stations that you could go up to, and you could do anything you want to. You could say, give me so many pieces of glass to here. Give me this, give me that, do this, do that. Okay, now what they did not do was to say, is that reasonable? All right, if you are taking glass off at a position and you can only take off 5 per minute and you're asking for 7 per minute to be cut and brought to you, what do you have? A mess. Everybody follow that? So the euphoria of building a line that can do anything came crashing down. Now, they didn't catch on to this right away. They didn't figure this out right away. And it almost bankrupted the company. And it's one of the reasons today that there is no Libby Owens Ford on the New York Stock Exchange. There is no Libby Owens Ford 500, biggest 500 companies in the United States. There is no Libby Owens Ford, period. One of the companies that disappeared from the face of the earth in the city of Toledo. Okay? Now you say, well, there's still Libby Owens Ford stuff around this and whatever. There is some, but it doesn't mount to anything. The company has gone away. All right? This is one of the reasons why it did. It's not the only reason, and I don't want to go into all the reasons why it went away because I don't know them all. A lot of poor business decisions, but this is one really bad one. So what's my point? This is a stretch, but you're a mechanical engineer, you're an electrical engineer, you're an engineer, right? And you think that you've got the world by the tail. You always have to ask the question, is this a good, what I'm doing now, is this a good decision from the point of view of the process? In other words, you have to think like an industrial engineer. All right? You don't have to promise me that you'll think like an industrial engineer, but it's your job to think like an industrial engineer. It's common sense. Most industrial engineering is common sense. But would you design a line that anything goes? If you think about it for a second, it sounds stupid because you can call more for more pieces than you can actually take off the line. You can do all kinds of stuff, but you can't really do it because why? You'll plug up the line. You'll do all kinds of bad stuff. So does everybody understand the rationale for making good decisions based on flow of line and all that kind of stuff? If you want to get into that deeply, you can. There are simulation packages. There are statistical simulation packages that will show you bottlenecks and flow. And one of the best ones is a company called Arena, which is a subset of Allen Bradley. So if you're into the Allen Bradley side and you open up the software packages from Allen Bradley, you will see Arena, ARENA. It is a package that graphically shows you all the parts that are going on the line, and it statistically shows them going at a statistical rate or whatever, but you can actually see those things. So that's my experience with LOF. That's also why I went back in industrial engineering to get a PhD as opposed to electrical engineering. Because I wanted to know some of this stuff. And there's not a lot. I mean, a lot of statistics. I hate to say this, industrial engineering is just the word common sense, but it is mostly just common sense. There are some things that you can do, and OR, operations research, is the one course that I would, if you have a chance to take OR, I would definitely take it, but that's about the only one that I would take from their side, other than the statistics courses, which you all have. You have to take anyway. So you get the statistics. You may not understand the statistics, but you've got them. They're really under your belt already. So again, I'm just telling you that the industrial engineering side of you has to come through at some point in time, or you won't really be a good engineer. Okay, so that's what that is. Okay, let's go back and talk about the faceplate, which is the other side of the this guy. Okay, so this is your we're going to talk about faceplates, and then I got sidetracked. So now we're going to go back the ball and tube. We're going to talk about a faceplate. Okay, so here's your screens. Okay, so this is the screen that's your base screen. Okay, now you've already got this information right here, most of it. In this arena right here, you have by the way, what is this called? This is historical data plot. This is a scope. This is your oscilloscope on your process, and it really is your ability to look into that process over the last minute, the last hour, the last day, and see what's been going on with that variable. Okay, so you can see anything that you want to on this screen. So now you can pull up off of the screen. You can pull up the various points. Now I'm going to pull up the properties of this because this gives you all the data that you really need. Okay. No, I think it's under this one right here. I think it's under this guy. And I'm not gonna, oh, there it is. There they are, right there. Okay, so these are your, this is your variables. Level SP, level PV, and fan percent. And these are your variables that you're gonna plot. So I'm not sure about that. Okay, this is the name of where they pull these variables from. Okay, this is a PID set point. That's what that is. This is your signal. Ball level PID set point. That's your this is the PID input. That's your this is the variable that you want. Now these variables are already scaled to 0 to 100%. So these are the ones you want to be able to show on your graph. These are the ones. These are the variables you want to be able to show. Let's go back and let's look at this for a second. So, it's been a while since I've done this, and I may stumble around a little bit, but in a in a faceplate, you have three variables. You might have two. You can sometimes get along without the set point, but you have the process variable. You have the process variable, the set point, and the output. Okay, and those are these variables right here. And that basically would, if you build a graph off of those three, you would basically be able to show that a linear graph going up and down. Now, some linear graphs only you must put a tick point at various places to show the height. Maybe little graph points like that or something like that. But they go from 0 to 100%, and you might show the graph like that. It's better if you have the graph and then you just fill in to a certain point, like it's to that level, and it goes to that point. That may be, if you can do that, that's the best way to go. Don't have it just like a bar that goes to that height and then stops. If you do, you have to put those tick points in. But that's up to you. But these are these three, and these are these three variables right here. What are the other ones? Well, there's the auto manual, okay? And there is your auto manual switch right there. So there it is. And you can click on one or click on the other. And let's just see what this says. That is a switch. That's true. It's a button. And let's see what it says. It's on an event. On release of the button. Okay, let's see what it says. PID mode select is the, okay, it's the, this is the button that you want to have. So you can copy this over on your other screen. So basically, you create a screen, use those three variables for these three graphs, these three linear graphs, and then copy the auto and the manual as buttons over here on the side, and you're done. That's it. Copy the auto manual button exactly as you have them here, and these three, and you've got enough for faceplate, and you're all set. That gets you 8 points, okay? Now the same thing for the other one, the tank over tank, except for the fact that the tank over tank does not work well, except for one of them. And it is kind of touchy. If you want to do that one, I'll give you 8 points for that one as well. But basically, it may never really officially work for you. So you may want to, how you want to say, if you want to create the faceplate for that one, I'll give you the 8 points. I apologize for it not working, and if you need help with it, I'll help you. The problem is that the pumps, the little pumps, have pretty much all died. There's one or two that work still, and they do put out water. The other ones do not. You see the red light coming on the driver board, which says that they're turning on the output, but there's nothing happening, no pumping of water at all. So I think they've all pretty much died. The other thing about the tank over tank is that the sensor at the top that's sitting there, that's looking down on the water, is a programmable device. So the high limit and the low limit are programmable, and some of them are set for going like this. Some of them are set for going like this. And again, it's a mess. I've got to fix that. But that's the only problem that with this. And I think most of them are like this way right here. But I'm not really sure. But that gives you a little bit of an idea about how to set up a faceplate, and that's extremely important. Okay. To be able to set up a faceplate is the part that we hadn't talked about before in the PID algorithm, and it's a very useful tool to have. Okay, so I got a little bit of time left, but not much. I want to talk just a little bit about another area of. Does anybody have any questions? Anybody lost or not, totally not following me or anything like that? Because I know this is a lot of stringed out stuff, but you've got from today, you've got a 4-point lab, 8.2 that you can do, and then now you've got this 8-point lab from chapter 19 that you can do. That's a faceplate lab if you don't have this already working, and that's all you need. And then you can do the other one as well. That gives you 16 points. That gives you some big heavy-duty points right off the bat on chapter 19. And I apologize for the one with the tank over tank, but it used to work, and it will kind of work if you find the right one. But again, there's a lot of problems with it, and if you get a faceplate on it at all, I'll give you credit for it. Okay. The other thing about this is you have to be able to call your program from this program. So this is the program that comes up. So you have to define one of your function blocks that calls the program with the faceplate, and then you can go back to this by hitting the button on that. But basically, it's a go-to function. You go to another screen, and you have to provide that with programming on one of your buttons. I would suggest you use F2. You've already got F1 for the one that is already there. F2 would give you the other one. So F2 goes to the screen. F2 from that other screen would bring you back to this screen. Okay, the go-to. So, what else can I give you that you get some points for? Well, we did talk about the camera systems already, and one of those camera systems is set up and working in 1100. It's the one that's over. If you were sitting there looking out the window, it would be to your left. It would be that computer just to your left. And that one works, and you can go through and do that one. I'll show you how to get to that. I'll show you how to get to those labs. So you're sitting here and say, now how do I get to these labs and actually get them to work? Well, here's how you do that. Under EET 4450, up here under Cognitive School, there is a Cognitive spreadsheet. Okay, so you click on that. No, I do not want to replace it. I want to get the thing already that's there. So I go to look at it, and it is download. It's Cognitive School. Cognitive spreadsheet. So here it is. Now, here is the manual, and here are the lab exercises. So basically, this is the manual that tells you how to do it. And then the lab exercises, if you go through 5.2, you are in. So 5.1 is the blob, and then 5.2 is the actual. And if you take that picture of that screen with all that 5.2 there, submit that, and you get your 8 points. That's a fairly straightforward lab. You have to go into the lab exercises and start with these three. Excuse me. This is the complete book, and you go through. You can kind of skip 1 and 2, but you got to go 3, 4, and 5. All right. So 3, 4, and 5. So it shows you about getting connected. You will connect. It'll connect you. The software and image acquisition, go through that. All you got to do is just look through it and read through it. Pat Max you have to do. Then you have to add to that the extract histogram, the extract and the histogram one. So then there's a detection of with the blobs. And then once you get the blob detection going, you will see a complete lab, and it's 5.2. If you stop there, take a picture of that. I know what to look for. I'll give you 8 points. Now, what is this good for? There's really 2 or 3 major brands in the United States of vision systems that are like this. Now you say, well, that's good for you, but I've been told that you can do this with AI and all that kind of stuff. Well, yes, they do have AI as well, but the AI is coming along, and I don't apologize for this because this is what we had for quite a few years, and we still don't have a lot of the AI built in. But what is he trying to say here? Pat Max is close to AI. It is not AI, but it's close. These tools are very useful tools for you to be able to inspect a part. And they set you up so that you can then look at the AI, which is coming along, and be able to use it. But this is what's been used for the past 15 years, and it's very powerful. These tools are very good. These won't go away, even with AI. These tools are not just going to disappear, okay? So here is the picture of the software for the without AI, okay? Inside Explorer. This right here is the Inside Explorer. This is the one with the AI in it, okay? Now you can use either one of these with those labs, and you can get through 5.2. They support the older version. They support all the stuff that's talked about in those labs. Here, that's all they do. But down in 1100, you have both of these. Up in 2350, you just have this one. So don't go up to 2350 and say, I can't find the deep learning one. It's not there. It's only in the one downstairs. So the one downstairs has both this one and this one, even though you will only be looking at the software that is viable with this one. And to be honest with you, this is the one that I was able to hook up the other night and actually get it to run. Everybody follow that? So if you can't get this to work, don't panic. Go back to this one, use it, and it will work. There's 2 types of cameras, and I'll go through that really quickly with you, and then we'll be done. Okay, there's 2 types of cameras. All right, Ted, get my sheet out here again. Okay, this is Cognics 101. These are the yellow ones. Okay, they have 7802s. This is the older ones. 3805s. These are the newer ones. And both of these are in North Engineering 1100. Only this one is in North Engineering 2350. Now, the software for this one is that's the older software. This newer software runs both this and this. Okay? The 3805 is a little fatter. It's a little wider camera. So this is a little fatter. This is a little skinnier. Other than that, they look exactly the same. And this is the one that works with the newer software, except for the fact that I haven't been able to get it to run lately on this one. But this one, I got it to run the other day with that one system. And I just sat down and it took right off with me. Now, here you go. It's 192.168.0.2. And they have to see that because that's the dongle address, the same address that you had on the PLC. This is the one that they link to. Okay. So they link to this, and they might be a 9 or whatever, but there's some other number like that. So you link to the dongle, and the last digit is the only that one is different from this number right here. That's worth 8 points. If you get it linked, 2 hours and you're done. Promise you, an hour and a half to 2 hours and you're done. But in those 2 hours, you will have learned a lot, and you will have learned a lot about how they see things, and how they actually look at things, and how they judge. What are we trying to do here? We're trying to pick a good part from a bad part, right? Come down the line at 700 parts per minute. That's what we're trying to do, seeing whether the part is up, the label's upside down. Is it up right side up? Is there a flaw in it? Does it have a gouge? Does it have is it a red label instead of a blue label, and all that good stuff? That's the kind of stuff you're trying to see is, all that boom, 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 boom stuff. Fast, and I do not apologize for the fact that it's not Keon's. You have two varieties. You have Cognis and you have Keon's. And they're running around here trying to beat each other up. And I didn't buy these. I was not the person that actually bought this. I was the person that they asked, and they said, "What would you do for vision systems?" And I said, "Cognex." I had no idea what I was saying, and I still don't, other than the fact that I do like them, and I do think they're important, and it's a skill. It's something that you can add to your resume, that if you booted up a system and gotten it to work with a Cognex camera, people take notice because it's a skill set. It's just like programming a PLC. Okay? It's a skill. And it's another thing to add to your resume. And I think it's worth it. I'll give you 8 points for it. Is it worth 8 points? I think so. You may not have to sweat quite as hard as you do on some of the other labs, but I think so. I think it's a good lab. You're not the only people that will be working on this stuff. You will be competing with these guys from the EET 4450 class who are doing this as well. They're doing it for a 7 lab. Like half of their labs are based on this. So they will be doing the same thing. So you'll be seeing them working on them. You'll be working on them. And enough of them will be set up that you can actually get these things to work, hopefully. The thing that has happened over the course of the last year in this fall was that people used them for other things, and they got all discombobulated. They're all over the place. They're here, they're there, and everywhere. And I'm not the one. I don't feel like I should be the one to have to put them back together again. You can figure this stuff out, and you have to put the 24 volts and 0 volts to the power supply, and I'll help you with that if you have a problem with it, but we can get you up and running. I'm confident that we can get you up and running, and I also know that one of the best support helplines in the country is the Cognex support helpline, and I've called it many, many times, and I've gotten a lot of answers, so I can do that, or you can do that. But anyway, that's 8 to 5, Monday through Friday. If you don't know me at all, basically take this to heart. I'm quick to call for help. I don't waste a lot of time. If I don't understand something, I can't figure it out. It doesn't take me long to call somebody and say, "Hey, how do you do this?" or "What do you do this?" Now of late, because Siemens has basically cut that out, you can't do that anymore. I used to call Siemens helpline a lot. They don't let you do it anymore. But my friends at ChatGPT have given me just about all the information that the people at Siemens ever did give me. So I'm happy as long as I can get my ChatGPT to work. By the way, I found out something else today, and this was that it was a ChatGPT, and I'm not sure if it works or not. I haven't tried it, but I think it works. You can take a get this, a cell or a group of cells in Excel. Let's say you have an array, okay? You have an array of cells that you build up to do something, as in Rubik's Cube. Okay, you build up a whole group of cells in Excel that does something, right? You can Control C, Control V, and plop those into a watch table in Siemens. Okay? Now, ChatGPT told me I could do that. I haven't tried it yet, but I believe them. Okay? So how would you take a recipe of moves and build them up in? It's much easier to do it in Excel, because what do you have in Excel? You have the ability to insert and delete. You can do that very easily, and you can build formulas in there, and you can have all kinds of stuff going on in there. And then once you've got the numbers in the spread cell and in those cells in that column, Control C, Control V, boom, splat, done. You are basically populating your recipe for how to solve the Rubik's Cube out of an Excel spreadsheet. So you see the synergy of the various products that you can use. Okay. Anyway, I hate to say this, but you got to think outside the box. I hate that, but that's old and it's trite and all that kind of stuff. And you got to think outside the box. Yep. Okay. Right. Next. Anyway, anybody have any questions? I think I've done enough damage for one night. Anybody have any thoughts? How many of you think that you would have done how many of you think you would have done what I did on that thing with that project? Just do it. How many of you would have just done it, or how many of you would have ask the boss? Any scaredy cats that are in there? You would ask the boss? You would have asked the boss ahead of time? Yeah. Honestly, I don't know whether I even thought about it or not, but I just did it. And I thought I was going to get away with it. I don't think I was going to tell him. But then I opened my mouth at the coffee machine. I opened my mouth and said, "Oh no, I didn't do it that way." And I was had. Take care. We'll see you.